in terms of areas under curves, what you want to do is it's always going to be the upper versus the lower, and in terms of the signed area, it's not the modulus, so it will be whatever this area is minus this area, and the actual area is going to be when we put like a modulus out the front here. So let's just kind of talk about the three different cases of if we're kind of considering graphs under curves. So what we're going to have here is we can have the first case, which is everything is above the axis, i.e. something like this, right? A to B. We can have things which are all below axis. So we can have something like this, where it's like that, and A to B. Or we can have something like where there's stuff above and below the axis, like this. So we have A and B. In this case, we can just integrate B to A f of x dx if we want the absolute area. For this one, what we want is we just negate it because it should be positive. So B to A f of x dx. Alternatively, you can also swap the terminals as well. It gives you the same effect. And this one, what we need to do is cut it at this point. Let's say that's x. So we'll say that's b to x, negative b to x f of x dx, and then plus x to a f of x dx. And that's going to give us the same thing. Cool, awesome. All right, so what about areas between curves? So same thing, we also have two types of things compared to the previous one, right? So what we'll have here is, if we look at these two ones, right? So there's no interchanging areas, which means we have something like this, and then like that, and then we have here A and B, and that's our area that we're looking for in there. And in that case, we can just go B to A, f, let's say this top one is f of x, and the bottom one is g of x. So that's just f of x minus g of x to give you the positive area. If there is interchanging areas, like something like this, and then we have, whoop, whoop, and we might, to make it even more interesting, let's say that's A, and then that point is B. So what we do here is we just need to kind of break it up into the sections. So top one's f of x, bottom one's g of x. So we break it up into this first section. We can break it up into like little sections. So we can start from left to right. So in this one, g of x is at the top, so g of x, right, minus f of x, and let's name these C, D. So it'll be g of x to f of x dx, and it'll be from C to A, and then we will plus our next one, so that's from D to C, and we'll have f of x minus g of x, and then we'll plus our last one, which is from B to D, and we can see that the g of x is once again at the top, so g of x minus f of x dx. Alright. Cool. Alright. So if you're finding the inverse area under the curve, what we're trying to do is like differentiate using the y-axis instead. So if we're differentiating something like a log, which doesn't have an antiderivative, what we can do is actually differentiate this section instead and then make a square and minus it from that. So it's another way that we can do it. So let's kind of talk about it using this log. So we have a graph of log 2x, right? Which means that we'll have something like this. So if we subbed in like 1 here, we would get that this is log e2. So if we tried to sub in a half, right? A half would give us log e1. So that's where it equals to 0. And we needed to find that because it's asking for the x-axis and it equals to 2. So you just need to find the intercept first. So it's from 2 to a half, and that's kind of the area that we're looking for. So what we're going to be going at here is now we also need to find out what log e2 corresponds to, and that will correspond to log e4. Now, we want to get this area here instead. So unlike an inverse function, we don't actually have to make it an inverse function. All we have to do is just rearrange for this. So it'll be e to the y equals to 2x, and then x equals to 1/2 e to the y, right? So we can kind of see that's going to be what that function part is there. So then what we can do is actually integrate it in terms of the y-axis. So we're going to go 1/2 e to the y dy, and we're going to integrate it from log e to the 4 and 0, right? Because we can see that's the y coordinates that would correspond to that. So what we will get from there is that this is a half e to the y. So a half e to the y doesn't really undergo any real changes, which is always good. So we can do that, and we'll get a half e to the y from log e4 to 0, right? So then from there, we'll get that this is going to be equivalent to a half e to the log e4 minus a half e to the 0, which is equivalent to log e4, that cancels out to just 2 minus a half, which is going to be 3 on 2, right? So then we have to kind of consider for what's actually going on in terms of our, like, this part of the equation, right? Because we've found this part. We found this section of the equation, but we wanted to find here. So what instead we can do is kind of form a square. So the square is 2 times log e4 as the kind of the dimensions of the square, and we just have to minus the area that we found instead. So we'll end up with just 2 log e4 minus 3 on 2. And that's how it rolls. Alright, in terms of the fundamental theorem of calculus, this sometimes comes up in like multiple choice type questions, so it's also a good thing to kind of look after. It's essentially just saying that if we have x to the a, all we have to do is add on that extra bit of x, because this is basically saying the amount of change that it's undergone from here to there. So that's the amount of y that's changed. So that's kind of the section of y that's changed, and this is the original y value. So that kind of tells you what the initial, like the end condition will be. So if we look at something like this, so dy dx equals to root sine where y equals to 1 where x equals to 0, then the value of y when x equals to pi on 3 can be found via evaluating. So what we can actually do here is when we look at this, we'll see that this is the equations that we have, and what we can do is we get the two functions first and we recognize, okay, so that's kind of the initial function that we're looking at, and what we can do is say, all right, so those two are the functions and this is my derivative and this is my initial condition, and then I can kind of name what this is. So then if we wanted to find pi on 3 and try to make that the end result, so what we would put in is y of pi on 3 would be pi on 3 to 0, because that's the next x coordinate we know, plus 1, right? Because that's the y coordinate that we know is coming across. It's kind of like integrating y on the other side. So you're saying the integration of 1 dy from y pi on 3 to 1 is equivalent to the integration of pi on 3 to 0, right, of your root sine x dx. And that's because that's basically what it is. Also, root dx. And then from there you can kind of see why the 1 goes across. So then if we try and do that, right, we'll eventually get that when we put this across, we'll see that it's equivalent to this, which is also going to be equivalent to option D here. Alright, another application that has to be considered is when we talk about arc lengths. So arc lengths are essentially when we talk about like the length of the curve, and you just plug into the formula. It's often like if they ask about how far did it have to crawl on the side, you just put it into the formula. So it can either be a parametric equation or just a straight one, and either way you can just sub it into the formulas. Okay. Volumes of several revolution, also something that gives people grief. Essentially just work out which axis you're working with and then just find the equation as appropriate and then sub it into the formula. The most important thing with volumes is that you keep it so that it's the same, like you know which equation you're using. So let's kind of talk about the different cases. So if we have volume revolving around the x-axis, so if we have something like this, we'll have something like this, a kind of a cone form like that, say like that, and that's our volume around the x-axis. And for that we just use our pi y squared because it's around the x-axis dx, and this is a b. And then volumes around the y-axis, a really common one is like making vases, so it might be this kind of thing, making a vase, right? And we just go from wherever, so our B and A are now here, so B a, and then pi x squared dy. So our x squared means that things are in terms of y, so our x in terms of our y. Right, hollow areas, so that's when we have something like this. So if we have two equations kind of being minus from each other, we have this section kind of being rotated around, what we're actually going to be doing is we're going to be grabbing each of them separately, right? So it will be pi b to a, so this is, once again, this is a is b to a, and then we'll have our f of x squared minus our g of x squared. It's not the whole thing squared, right? Because it's not the difference part squared. It's each of them individually squared. So because you're making a donut essentially, rather than you're kind of finding the volume, the outside volume, and then you're finding the inside volume, right? Because that's what the g of x part would be, rather than them being put together and then finding that area that just goes around. You'll find each of the volumes separately and then minus, but because they're over the same terminals, we can kind of combine them together. All right, and this last one, which is hollowed areas and then hollow and a solid area, is if we have something like this. So once again, but we're going over this whole thing, and all we have to do is just split that. So we do the solid area first, right? So that's f of x or whatever, and then we do the hollow area separately. Because before this, we only would have needed really to use f of x, the outside function, versus this one where g of x kind of comes in there. So you can split it into two components. Okay, cool. Alright, so that's how our volumes of solid revolution can work. And so, for example, if we considered this being rotated around the x-axis from from x equals to 0 to x equals to 16, we would put in the terminal 16 to 0 and put in the equation. We don't need an extra pi there. And essentially, it would just give us that when we square it, we would get that this is going to just be derivative of x, right? Because it's x squared, root x squared, so we'll get that, and then essentially from there onwards we can get an equation. So it will just be from a half x squared from 16 to 0, so, and that times by pi, so we'll get a pi, and 16 times 16 is 256, yep, so 256, so it'll be 128 minus 0, so just be 128, and don't forget about units cubed. Alright, so if we talked about rotating it around the y-axis instead, what we would have is like rotating around the y-axis, so we'll have this instead. So now we want y equals to 4 and x equals 0, so that's 0 to 4 for this equation, right? So we put in the terminals, 4 to 0, make the y squared instead. So this is just an equation of y equals x squared, so x would equal to plus or minus root y. We can see we're using the positive branch, so it's just going to be our x equals to root y, and then once again it gets squared, kind of very similar to the previous one. We get a half y squared of 4 to 0, so that's going to be pi times 8 minus 0, so it's just going to be 8 pi units cubed. Alright, surface areas of revolution, very, very similar, derived from kind of looking at derived from doing this thing where called like frustrums or something, and then we could basically just cut up the equation into little slices to find the lengths of the curve. So it's kind of like the baby of lengths of curve and volumes of revolution. Okay, so what we can do here is we can pop that equation in for us to use, and we can do the same thing for this one. So we need to find what f dash of y is as well. So we said that x would equal to root y, right? So f dash of y dx dy would have equal to 1/2 of root y. So when we kind of try and sub that into there, we'll get this as 2 pi 4 to 0 root y times x 1 plus 1 over 2 root y squared dy. And then from there, so there's not actually many that you can do by hand for these ones, unfortunately. So get that 2, 4, 0, and you'll get that this is going to be root y times by, this is going to be a 4th y, right? So in order to kind of compensate, you're going to get 4y plus 1 over 4y and dy. So then if we kind of times out that root y, because the root y is at the bottom there, we'll get this is 2 pi 4 to 0, and the root y should cancel out. So we're going to just get that's going to be 4y plus 1 over 4 dy, which now we can kind of use our substitution methods to do, right? Awesome. Yeah, and we can kind of progress from there. All right, so in terms of applications of integration, the main thing is that we just use it for functions that we don't recognize or we know that doesn't have direct integration. And then we just make x the subject, and we can draw and shade and kind of like always just kind of visualize what you're trying to find. These are the equations that you can use. I would recommend having these on your bound notes somewhere just to kind of have a look and be able to see.